Right, so let's continue. So this is part 2 of chapter 17, aromaticity. I had some issues with the internet connection, so that's why the previous video, it looked like it was recording, but for some reason the image froze and only my voice was running. So I'm re-recording the last 30 minutes of that video, part 1. So I labeled it as part 2, but it's really the continuation of aromaticity, chapter 17. Okay, so where we left off at this problem, right? In this problem, the big question was about which of these two compounds, pyrrole or pyridine, pyrrole and pyridine. By the way, pyridine is a very toxic solvent. Which is has some acidized properties. Right, so we have pyrrole and pyridine. So which of these two compounds is more basic? Okay, and remember that for all these aromaticity problems, we always have to put the molecule in action, okay? So for example, if they're asking you, is this basic? Then make it behave as a base and see what happens. If the problem is asking you, is this compound acidic? Well, deprotonate it, make it behave as an acid, and then evaluate the conjugate base. In the case of the base, then you will evaluate the conjugate acid, okay? So we have extensively discussed, and then this is it should be your fourth chemistry class in which you guys are exposed to acid and bases, and you know that an acid gets converted into a conjugate base, and we also know that a base is converted into a conjugate acid. So in this case, which is more basic, so I'm going to make it react with an acid, and I'm going to protonate it. Of course, in this case, the protonation will occur at the lone pair of electrons, right? So there's only one available lone pair of electrons. Therefore, that's the one that's going to behave as a base. Okay, so let's see. Now has a charge, right? Because the nitrogen here used to be neutral. Now, once it gains that hydrogen, it will be plus. Same thing with the pyridine. I will protonate it. The pyridine will get protonated by the nitrogen. Of course, the nitrogen with the lone pair of electrons will catch that hydrogen, right? So we have this. Of course, the nitrogen is going to be positively charged. Now, these two are the conjugate acids. So I have to see which of these two is more stable. Okay, so for example, let's do the aromaticity, right? Remember in chapter 17 about aromaticity. So we will see, is this compound a ring? Yes, it's a ring. Is it conjugated? Okay, let's see. Charge, single, double, single, double, single. Yes, conjugated. Okay, is it planar? Where we always say that we're assuming that all our compounds are going to be planar. Now, the next one is the Huckel, right? The Huckel equation, the Huckel rule. So we have two formulas for that. So we have the 4n plus 2, and the 4n is equal to the number of pi electrons. So let's apply the resonance, the aromatic. Okay, number of pi electrons. How many pi electrons do we have in pyrrole, right? In the conjugate acid of pyrrole. So you have 2 and 4. Nitrogen doesn't have electrons anymore. So it's only 4. So no, it doesn't follow the aromatic Huckel. But let's see the anti-aromatic Huckel. Yeah, you have the anti-aromatic Huckel. So this compound is actually anti-aromatic. Okay. Do you think that pyrrole will like to behave as a base? No, because if it behaves as a base, it will turn out anti-aromatic. So therefore, the equilibrium will be shifted more to the neutral form, not to the basic form. Okay, no, I mean, not to the one that behaves as a base. Let's see pyridine. Who knows? Maybe pyridine doesn't want to be a base either. So let's evaluate the aromaticity ring. Yes, conjugated, double, single, double, single, double, single. Correct. Good. Planar. Yes, planar. You would say, like, Professor, what happened with that charge? Is that charge also part of the resonance? No, in this case, no, because it is the molecule is fully conjugated inside of the ring, even without the charge, right? You can see here, double, single, double, single, double, single. The presence of the charge does not affect the resonance, so then you don't have to count it. Next is the Huckel, or n plus 2 is equal to the pi electrons. 2, 4, 6. Nobody else has electrons, 6, and is equal to 1. Therefore, the molecule is aromatic. Okay, so here we can see that the conjugate acid turns anti-aromatic, and this one is aromatic. So therefore, which one is the species that is more basic? Of course, pyridine would be more basic than pyrrole. Okay, so we have some other, one more about acid and bases. Let's see. Which of these two compounds is more acidic? More acidic. Once again, anytime that they ask you about acidity, you have to make it behave as an acid. So you guys have to create the conjugate base. So how do I know which hydrogen should I extract? Remember, according to the Ario principle, right, it's about atom. I cannot use atom because here there are all CHs. Resonance, there is resonance. So you have to do it based on resonance. Which of the hydrogens will give you a better resonance? Better resonance will be, of course, with this hydrogen. Why? Because if I remove that hydrogen, if you remove the hydrogen, you will get a minus there, and that minus is conjugated. Lone pair, single, double, right? It's conjugated, so that's why it will do it at that point. If you do it here, it will not be conjugated. It's not going to be conjugated in this position either. Here, the same thing. You have to always look for the allylic position. We discussed that a few times, allylic position, and the allylic position is this one, the one that is conjugated to the double bond. So here will be my hydrogen. I have to deprotonate it. Okay, so now that I have my conjugate bases, right? Both of them are conjugate bases. I have to see which one is more stable. Let's analyze aromaticity. So ring, yes, ring, yes. Conjugated. Actually, this one is conjugated, right? So you guys see it. It's conjugated. Lone pair, single, double, single, double, single. Yes, conjugated. Is this conjugated? Let's see. Actually, this one is not fully conjugated. I have lone pair, single, double, single, double, single, single. So now it's not conjugated. So just because of that, this compound becomes not aromatic. Okay? Yes, this one is already disqualified. It's not anti-aromatic, it's not aromatic because it needs to be conjugated. Let's continue with this guy, right? Who knows? Maybe it fails the next steps. Planar, okay, well, we're assuming that it's planar. What about the Huckel formula for aromatic? For n plus 2 is equal to the number of pi electrons. 2, right? 4, and 6. 6 n is equal to 1. Therefore, it is aromatic. So you ask me which of these two compounds is more acidic. Of course, I will tell you that this compound is more acidic. Why? Because this compound generates a conjugate base that is aromatic. By the way, anytime that you guys have to are asked that question, you should not just say like, oh, because it's aromatic. That's not the answer. Okay, so whenever you are being asked like which of those two is aromatic, you have to say that the conjugate base that is produced, right, from that acid satisfies the rules of aromaticity. And you have to show me how it is arranged, the checks, the procedure, ring, conjugation, planar, and Huckel. It's not just by telling me like, oh, this is aromatic. No. Okay, so it's aromatic, but you have to support it. You cannot just say like, oh, the moon is spherical. No, you have to tell me like why do you think it's spherical? Because it has a radius, it has a circular surface. It is many things that it is. The answer is not just writing in one word automatic. No, the an appropriate way how to answer a question of this type, right? Which of these two is more acidic? Is just by explaining, like showing your two conjugate bases and also do the analysis. That's why I'm doing the analysis. Otherwise, in this explanation, I will just be telling you like, oh, guys, this is aromatic. You figured it out. No, I can't. We cannot make those assumptions. So that's why if I'm showing you the procedure, how to do the analysis for, acid and bases, solubility, polarity, charges, etc. Of course, you guys have to use the same protocol that I'm showing you. Okay, so please don't just simply right. And I'm telling you this because in the previous semester that has happened to me. That has happened many times that, students just simply write like, oh, because it's aromatic. And they don't even say that the conjugate base is aromatic. They just like write aromatic. And then sometimes they are not wrong, but it's not the appropriate way how to answer, a problem that needs really definitely needs more elaboration. Right? Okay, so that's it about aromaticity. I will do like few more examples for you guys to analyze if a compound is aromatic or is not aromatic. Okay, so I will draw them here for you, and you will do the analysis if they are aromatic or not. Actually, this is a nice one. Okay, that this one, and the last one is this one. All right. So if you have these four compounds and they're asking me if they are aromatic or not. Okay, so let's start with the first one by one, and you guys tell me. Is this compound a ring? Yes, it's a ring. Is this compound conjugated? Let's see. Lone pair, single, double, single charge. Yeah, it is conjugated. Yeah. Said professor, but it's not conjugated maybe this side. Well, I mean, it doesn't have to be fully. Every single atom of the ring has to be conjugated. That doesn't mean that you have to do like the 360 cycle. No, sometimes we can go like this, like half moon, right? As long as every single atom is conjugated. For example, you will tell me like here I cannot conjugate here. It's lone pair, single, lone pair. How can I conjugate lone pair, single, lone pair? That's not a conjugation. True, it's not a conjugation, but this one is conjugated to this, and this one is conjugated to this. So all the atoms are conjugated in some extent. Okay, so that's the important thing is that you don't have to do conjugation. That doesn't mean that you're gonna make circles with the resonance. No, not necessarily. Sometimes you can go like clockwise, and then at some point return counterclockwise, clockwise, counterclockwise, and that's enough to be conjugated, right? Planar, we're assuming that is planar. Now let's do the Huckel for aromatic. 4n plus 2 is equal to pi electrons. How many pi electrons? 2, 4, 6, 8. Okay, what happens with this lone pair of the sulfur? The second lone pair, it does not participate. Sulfur can only participate with one lone pair. The other one is out of the plane, so it cannot do resonance. Okay, so it will be 8. 4n is equal to 6, and is not a whole number, right? It is 1.5, and that's not a whole number. So it's not, is it aromatic? No, it's not aromatic. Let's do the next analysis. 4n is equal to n is equal to 2. Now that is anti-aromatic. So the compound is anti-aromatic. You still guys have to report it. In real life, the molecule is not going to be is not going to stay as an anti-aromatic. What is this compound going to do? Oh, well, maybe the compound is going to be very basic. This one is going to be very reactive. Or maybe it's not going to be planar anymore, most likely, right? It breaks the planarity of this geometry. Many things that the compound can do. Okay, so let's do the next one. Is this a ring? Yes. Conjugated, charge, single, double, single, correct. Is it planar? We're assuming that it is. Let's do the Huckel. Now let's do the Huckel for anti-aromatic. 4n is equal to 2 and 4. N is equal to 1. Therefore, this compound is also anti-aromatic. Okay. Next one. Here we have a radical. Look at that. It's been a while, radicals. We haven't really seen radicals that much. Okay, so radicals, yeah, the problem with radicals is that they will always give you an odd number of electrons, right? It's an odd number of electrons, and then it's not going to satisfy any of the Huckel equations, right? No, they will not, none of them will align, because if you look at the equations, they are all assuming that the number of pi electrons are even numbers, right? So if they are not even numbers, then they are not going to be any of the two options, right? So they cannot be aromatic and they cannot be anti-aromatic. But let's prove it. Let's see. Is it a ring? Yes. Is it conjugated? radical, single, double, single, radical. Well, radical does do resonance, so does have resonance, so it is really conjugated. Is it planar? Let's assume that it's planar. Let's see the formula for n is equal to how many pi electrons? Here I have 2, 3. N is equal to 0.75. So no, let's do the other one. For n plus 2 is equal to 3. For n is equal to 1, n is equal to 0.25. No. So the molecule is not aromatic. Now let's see the last one. In last case, we have a cyclic compound. Yes. Is it conjugated? Charge, single, double, single, double, single, double, single, charge. Perfect. They're all conjugated. Planar, let's assume it's planar. So now let's use the formula. Let's do the anti-aromatic. For n is equal to pi electrons, 2, 4, 6, 8, 10 pi electrons. No, it does not satisfy the anti-aromatic, right? Just try to figure out 2.5, right? No, it's not anti-aromatic. What about the aromatic? For n plus 2 is equal to 10, n is equal to 2. It is aromatic. So this compound is aromatic. It works with aromaticity. All right, great. So now, for more problems, I mean, to be honest, guys, for this particular chapter, we have a lot of resources available online. So you want to see more problems like this, aromatic, anti-aromatic. First, you can go to the textbook. It will have many cases that you can explore one by one, right? The other one is online in internet. You know, you guys have tens or hundreds of examples for aromaticity or anti-aromaticity. So it shouldn't be an issue for us really to find more examples for, this type of problems that determine if a molecule is aromatic or not aromatic. All right. All right. So let's continue with the last part of the chapter. The last part of the chapter, we have, well, here are some more examples for acid and bases. You see here, explain why this compound is acidic, right? It's acidic because once it gets deprotonated, now it becomes aromatic. But of course, you guys have to do the analysis of the aromaticity, okay? So here is another example, the tropylium ion. So determine if this compound is aromatic or not. So we have to do the analysis. So here it explains the localization, the resonance formation in this particular compound, okay? Yep, the pyridine pyrrole example that I show you is also in here. Basically, all the example very similar. Fused rings. In the case of fused rings like naphthalene, anthracene, and phenanthrene, right? So they're just benzene rings, fused. Are they still aromatic? Yeah, absolutely. So here you have 10 electrons. Here you will have 10, 14 electrons. Here, well, also 14 electrons, right? So we have 14 pi electrons. And of course, they're aromatic. They tend to be a solid. Naphthalene is a solid. Anthracene should be a solid. And phenanthrene is also solid. So all these compounds are solids, but now because they have, higher molecular weight, right? So definitely they are more, they have. And also, since they have like an extended number of benzene rings, the aromatic interactions, right? The aromatic forces are very strong, because now it's 3 rings, right? 3 fused rings, which are interacting. So definitely the interactions are going to be way stronger. The aromaticity also, it gets better. Why? Because now you have more pi electrons. Remember, the more pi electrons you have, the better resonance. The better resonance, the stronger is going to be also the aromaticity. All right. So here is what is the next part, is that we will learn 2 reactions. One is the oxidation of benzene rings. Okay, so at some point we were saying that benzene rings, or aromatic compounds in general, they're very stable. They don't get oxidized. The only thing that you can do a reaction maybe is under high pressure with hydrogen, a high temperature, you can reduce it to get rid of the benzene ring, right? So that the double bond disappears. In the sense of bromination, it does not give it any reaction, but you can oxidize the side chains, the alkyl side chains. Right? So you see this sp3 carbon, this sp3 carbon, well, those are called benzylic positions. Benzylic. These hydrogens that are sitting on the ring, they are called phenol. phenol positions or aromatic hydrogens. But the ones that are right outside of the benzene ring, they are called benzylic. So if you guys have hydrogens in the benzylic position, okay, so they are able to, I mean, they are prompt to be oxidized. Okay, so benzene ring, plain benzene ring with sodium dichromate, sulfuric acid, and water, there is no reaction. Plain alkanes in dichromate, sulfuric acid, and water, there is also no reaction. But what happens when we have this side chain attached to the benzene ring? Does it get oxidized? Yes, it does get oxidized to carboxylic acid. Okay, Professor, here this side chain has three, four, five, six, seven carbons. This one has 4. Does it matter the length of the side chain? No. The length of the side chain does not matter. That means that if you have 1 carbon, it will oxidize benzoic acid. 2 carbons, benzoic acid. 3 carbons, benzoic acid. Isopropyl, benzoic acid. Propyl, benzoic acid. Butyl, benzoic acid. So no matter what is the size, the length, or the branching of that side chain, it will always give you benzoic acid. Professor, what happens with this rest of the side chain? Because you are cutting it at, right? You're cutting it at this position, right? What happened with this carbon, and this carbon? Yeah, they undergo some other type of degradation. Mostly they will go to the gas phase, maybe carbon dioxide, carbon dioxide, carbon dioxide. So we don't really care about what happens with those carbons, okay? So the only thing that we care about is what happens with the first carbon, this one, which is called the benzylic hydrogen. Okay, what is the requirement? That it has to have at least 1 hydrogen. Okay, so what am I trying to say with that, right? That statement that you need at least 1 hydrogen. That means that if you guys have terbutyl will not oxidize. Okay, you see that this carbon has no hydrogen. So if you guys do a reaction with sodium dichromate, sulfuric acid, and water, here there will be no reaction. Okay, Professor, what about if I have benzene, and then you have here have a methyl? Okay, so you have a methyl here, then only the methyl will get oxidized. Even if you have excess, yes, even if you have excess, okay? This one will not oxidize, but this one will do oxidize. So the benzene ring that you guys are getting will have the terbutyl untouched, it will not react, and then the other side will be the carboxylic acid, all right? You need at least 1 benzylic hydrogen. That's the minimum requirement for this reaction. What if I have 2 side chains? Yeah, you can also have 2 side chains. For example, if you guys have this ethyl and isopropyl, right? And I do the reaction with sodium dichromate, sulfuric acid, and water, right? Then you have this, then excess, right? Assuming this excess, yeah, is this one have hydrogen? Yeah, it has 2 hydrogens. Okay, at least 1. Does this one have a hydrogen? Yes, has 1. Okay, so if they have a hydrogen, they get oxidized. Okay, so both of them will become carboxylic acid. COH, COH. What happened with these other methods? Nothing. Do I have to write the side products? No, just carboxylic acids. Okay. What if, Professor, you just show us that naphthalene? What happened with the naphthalene? The naphthalene means that they will also get oxidized in this case. No, should I consider that as a side chain? No, it's not side chain. They are fused rings. So it's really like a large benzene. Let's call it like that. And naphthalene is really like a large benzene. So the aromaticity goes around the 10 atoms. So you cannot just oxidize here and here. No, there is no oxidation here. What if I have a methyl here? Yeah, you have a methyl. Yeah, that's a different thing. Then that methyl gets oxidized. But it gets oxidized in the presence of the naphthalene. Is the naphthalene the aromatic core that allows that methyl to be oxidized? Okay, very fun, right? So the other, this one is, if you notice, the oxidation is in acidic conditions, right? Sodium dichromate, sulfuric acid is in acidic conditions, but there is also another one, another oxidation in basic conditions. You can do exactly the same thing. Let's say I have ethyl benzene, and now the reagent will be potassium permanganate in water and heat. I think it's heat. Let me double check. It's on the slides. You guys will see it. Yeah, heat, right? Water, heat, and water. Okay, so the water, heat, and water, right? Potassium permanganate is a basic salt, so it will produce the carboxylic acid, but deprotonated because remember it's basic. So you guys will have carboxylate. This is called carboxylate. So in a second step, what I need to do is add acid. If I add acid, then that carboxylate will get neutralized to carboxylic acid. Okay, so whenever you guys do potassium permanganate in water and heat, don't forget that then there is a second step. You need to do a second step to neutralize that negative charge. So now it becomes carboxylic acid. You don't have to do that if you guys do the acidic oxidation, because acidic oxidation comes with the acid already. The cocktail has the acid, so you don't need to do any additional protonation. But potassium permanganate, it has two steps. Step one, permanganate water. Step two, acid, right? It's very important that we remember to always label step one, step two, right? For example, this one doesn't have one and two. That means that everything is added together. If you have one and two, that means that first is this one. The intermediate of this reaction will undergo step number two, right? So that's the meaning of using this one and this two, and then here no numbers. Okay, good, clear. So there's not much synthesis questions or reactions. They are very simple. Right? We will use these reactions mostly for next chapter, chapter 18, which is aromatic substitution. That one has a high content of reactions. So definitely we will use it in, with this oxidation. Next is the reduction. Okay, so we went over that reduction step, right? Very early. So the only way how you can reduce benzene is in hydrogen is by using a high pressure and also high temperature. It's too high, right? So imagine 100 atmosphere pressure is, at the sea level right now in New York City, we have 1 atmosphere pressure, sea level. So I would say you would need to go meters and meters under the water in the ocean to undergo that pressure of 108 atmospheres. It is a lot of pressure. And now it's even with heat. It's a lot of heat. Also, 160 degrees is not low. Okay, so definitely at 150 degrees, the benzene might be a gas, but maybe with that pressure will still stay as a liquid. It depends, but see, so it is an exothermic reaction, but the reaction conditions is really high, right? It's a high penalty. Okay. Another way, well, the regular conditions for hydrogenation, right? With H2PT at a regular pressure and room temperature, right? So if you put a styrene, for example, the benzene will not change. The benzene because it's too stable. Remember, to reduce the benzene, you need these conditions right here, which are not present here. So the benzene will not react. But the allylic, sorry, the vinyl, right? The alkene side chain will do get reduced. Okay, but there is one reaction, which is the one that we are learning right now, is the Birch reduction. There is a typo here. Please correct on your slides. So this one should be cyclohexadiene. Right? 2 cyclohexadiene is 1,4. 1, 2, 3, 4. Yeah, 1,4 cyclohexadiene. Yep, so 1,4 cyclohexadiene with it should be 2 double bonds on the side. So the reaction is metal sodium in methanol in the presence of liquid ammonia. Ammonia is present. And then here is the mechanism, but we don't need to do the mechanism. It's a partial reduction of the benzene ring. You can see that you started with 3 double bonds, and now you have 2 double bonds only. So you have a partial reduction. Can I use H2PD to remove this hydrogen? Yeah, of course. You can add hydrogens to those double bonds with H2PT, and the reaction will proceed. Right? But the important thing is that you are gaining 2 sp3s. Here, everybody's sp2. This one involves sp3. The mechanism involves radicals. You guys can see here a radical. I'll circulate the radical right here, radical right here, okay? And then the oxidation of the metal sodium. Sodium is used in the native state because it provides the electrons. Okay? It oxidizes pretty easily. That's why it's used in this reaction. We don't need to know this mechanism, but the only important thing is that you guys will have to remember the electrodonating groups and the electron-withdrawing groups. We went over these groups in the previous chapter, chapter 16. Chapter 16 about conjugated dienes and pericyclic reactions. I show you at some point what are the most common, right? Electrodonating groups and the other electro-withdrawing groups when we were doing the Diels-Solder reaction. So the same groups that are electrodonating and electro-withdrawing that we use for chapter 16, they also apply for this reaction. Okay, later on, I will show you, actually, because I just finished also recording the next chapter, you guys will receive this table, okay, which on chapter 18 about aromatic substitution reaction. Here there is a table that condenses the electro-withdrawing groups and the electro-donating groups. Here is the division line. So all these guys are electro-withdrawing groups and all these guys are electro-donating groups, okay? Actually, no, I think that even up to here, my bad, here, right? So I know the halogens are electronegative. They are kind of in the borderline, okay? So they have some electronegativity, they are electro-withdrawing, but by resonance, they're electrodonating. Yeah, that's kind of like it's a very tough decision in the case of the halogens. Halogens, they have both aspects. So they can donate through resonance, but because of their electronegativity, they are electro-withdrawing. So they're kind of like in the interface between the two. But these are definitely very solid electrodonating, and these are very solid electron withdrawing groups. Okay, so just remember, maybe screenshot this. We are not allowed to use this table during the exam and the quizzes, unfortunately, but we have to get familiar. So please. All right. So what are we learning about that? Because if you guys have a benzene ring that has a methyl, okay, and I do the Birch reduction, which is sodium and methanol, in the presence of ammonia, liquid ammonia, right? I have to decide, right? Because I can have two options. I can have the methyl here or the methyl here. Right? Two options. The methyl can be sitting on a double bond or the methyl can be sitting on the single bond. Where is it? Well, I have I came up with a letter, association. Methyl is an electron donating group, right? Electron donating group. So donating with a D. That means that the methyl, the electron donating group, has to be sitting on a double bond. Okay, D from donating, double bond. So that means that this is your product. This is not observed. So this one should be the product that you are obtaining. Okay, so what about with the electron withdrawing group? Yeah, the electron withdrawing group, that means that this one has to be attached to the sp3 or the single bond. Well, you have three peaks, right? Three peaks sp3. Yeah. So what is an electron withdrawing group? For example, benzene ring, and you have nitro, right? Nitro. I do the Birch reduction, Birch reduction, and then the nitro has to go to the sp3 carbon. Okay, makes sense. Good. What if you have, because I know that you're going to ask me, Professor, what if I have two groups there? Let's say that I have a methyl and I have a cyano. Cyano is an electron withdrawing group. This one is electron withdrawing group. Methyl is electron donating group. Well, you draw your product with double bonds. And remember that the CH3 is the electron withdrawing group cyano is the electron withdrawing group, right? Cyano. So therefore that one has to go to an sp3. And the CH3 has to go to the sp2 or the double bonded. I can do it this way or this way, doesn't matter. But the CH3 will go there. Okay, always make it match. The electron withdrawing group should go to the sp3 carbon. The electron donating group has to go to the sp2 carbon or the double bonded, but do not lose the sequence, right? Cn next to CH3, Cn next to the CH3, and that would be the solution for this problem with the Birch reduction. Remember, we're not doing the mechanism. It's too much. Okay. So this one is placing a little bit more detail, right? So no mechanism is only more details. Here they have acetophenone. Acetophenone is an electron withdrawing group, right? As an electron withdrawing group, it will go to an sp3 single bonded, and then that's what you guys see, right? So that the acetophenone goes to the single bonded. This one that goes to the double bonded is not observed. If you guys have both groups, yeah, you have to make it match as should be. All right, so this one is the condensed chart with all the reactions. Here there are some reactions that we should know, right? From organic chemistry 1, we can do some substitution. MBS, when you brominate the benzylic position, which is equivalent to the allylic bromination. This one is the, well, elimination reaction. Well, these are all just all reactions. This one is the new one, oxidation. Please make sure that we remember this one. Okay, this reaction, the Birch reduction, okay, here another typo. Well, another typo. Double bond. Okay, so it should be double bond here. Or is it alkene? Let me think. No, 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 my bad, my bad. Yeah, no, that one is the catalytic. That is not the Birch. My bad, my bad. This is not the Birch. This one is the regular reduction. Did I make the same mistake here? No, no, no. Here it is Birch. This one is Birch because this one has to be with the two double bonds. Okay, that's the Birch reduction, right? So with the electro donating goes to the double bonded, donating D double, and then electro withdrawing with sp3 goes to the single with the single bond. All right, so that's it. So hopefully this is this half-hour recording to compensate. This is part 2 for chapter 17. Okay, so as usual, please let me know if you guys have additional questions. I will see you soon for the next chapter about aromatic reactions, substitution reactions. Okay, bye-bye.